In the last video, I used a hash set to control what went in a set and what didn't by manipulating the equals and hash code methods. In this video, I'll be explaining set math or set operations, first what they are, and second, why you'd want to use them. When you're trying to understand data in multiple sets, you might want to get the data that's in all the sets, that's in every set, or the data where there's no overlap. The collection interface's bulk operations, add all, retain all, remove all, and contain all, can be used to perform these set operations. Sets are often represented as circles or ovals with elements inside on what is called a Venn diagram. Here, I'm showing two sets that have no elements in common. This Venn diagram shows some of the cartoon characters of the Peanuts and Mickey Mouse cartoons. Because the characters are distinct for each set, the circles representing the sets don't overlap or intersect. This diagram shows two sets of characters that do overlap. Let's say that Goofy and Snoopy have guest appearances in the other's holiday special show. The intersection of these sets is represented by the area where the two circles, sets, overlap and contains the elements that are shared by both sets. Goofy and Snoopy are both in set A and set B, in other words. Venn diagrams are an easy way to quickly see how elements in multiple sets relate to each other. The union of two or more sets will return elements that are in any or all of the sets, removing any duplicates. These may look familiar because these are the sets I had at the end of the last video. Our email set had Linus, Daffy, Mickey, Minnie and Robin Hood. Our phone set had Lucy, Maid Marian, Charlie Brown, and also Mickey, Minnie and Robin Hood. The slide shown here is showing my two sets, names on an email list and names on a phone numbers list. The overlap are names that are on both lists and includes Mickey and Minnie Mouse and Robin Hood. In the example shown on this slide, all names on the email list and phone list will be included in a union of the two sets, but Minnie, Mickey and Robin Hood, which are the only elements included in both sets, are included in the resulting set only once. If you have any experience with structured query language or SQL, you may already be familiar with the union command, which joins two datasets in the same way described here. Java doesn't have a union method on collections, but the add all bulk function, when used on a set, can be used to create a union of multiple sets. Getting back to the code from the last video, I left off with two sets, email contacts and phone contacts. A union of these two sets should give us a set that consists of distinct contacts by contact name. To perform a union, I can use the bulk operation add all. I'll first create a new set called union AB, a hash set with a no args constructor. I'm going to stick to the convention on my slides where A is the email set and B is the phones. I'll use the add all method on the union AB set to add first email contacts. Then for phone contacts, lastly I'll call print data with a header saying this is the union of emails A and phones B. There's a special ASCII character, 222A, that represents the union character that looks like a U. I'll use that. Note that IntelliJ is highlighting that Unicode character and prompts me to replace it with the actual character, so I'll do that. Running this code now, I get the union of these sets, and as you can see there's no duplicates by name. These operations combine the two different sets of contacts into a single set of unique contacts. I have lost multiple phone number and email information though as a result of this. But if you ever just need a distinct set of elements from multiple sets, this union operation can give you that information. At this point, it would be nice to know which contacts overlap the sets. This information might allow me to process those records in a different way, perhaps capturing the additional emails and phone numbers, for example. The intersection of two or more sets will return only the elements the sets have in common. These are shown in the overlapping area of the sets on this slide, the intersect, shown in green, and includes Mickey and Minnie Mouse and Robin Hood. Let's try this out with our same two sets. I'll start out by creating a local variable, a set I'm calling intersectAB. I'll again assign that a new instance of hash set, but this time I'm going to pass my email contacts set directly to that constructor. I'll execute retain all on the intersectAB set, passing it the phone contacts, and I'll print the result. The ASCII character for the intersect operator is 2229. It looks like an upside down U, and I include that as part of my message. I'll again take IntelliJ's suggestion and just convert the Unicode escape sequence to the actual character. On the first line this time, I'm simply passing my first set to the constructor of my new set. In fact, if I control click hash set there, the code is displayed showing you how it's implemented. And you can see this constructor simply calls add all there. Did you notice that it's creating a new hash map, assigning it to a map field on this hash set class in the first statement? I said before that the hash set uses a hash map in its implementation, and this is obvious here. These two classes are tightly interwoven in current versions of Java, but regardless of the underlying way the hash set implements its collection, and there's never any guarantee in Java that the implementation won't change, the behavior of the hash set will be consistent. This means duplicates aren't supported, the collection won't be ordered, and hashing will be used to provide close to constant time access. Okay, so getting back to the main method, the other thing to see is that I used retain all and passed into it the phone contacts. Running that code now, I get what's called the intersection, where the two sets intersect, and the result is the elements the sets have in common. This gives me the three contacts that are on both lists, Robin Hood, Mickey and Minnie. Notice that the contacts all have emails, and that's because multiple records weren't added, and it's the first record that's added that remains in the set. In other words, a duplicate element won't replace the current element. In this case, when I added the phone contacts for Mickey, Minnie and Robin Hood, those records were ignored because the set already had records for them in it. I can switch the order of the way I intersect around, and I'll show that to you next. I'll copy those last three statements and paste them below. I'll change my set name to intersect BA in all three statements. I'll pass phone contacts to the constructor this time, so those are the first set of elements included. I'll change phone contacts to email contacts when I call the retain all method. I'll also change my output to reflect this change. I'll run this now to check the results. I get the same set of three cartoon characters, Robin, Mickey and Minnie. The extra data that wasn't included in the equality test is different here though, so now I get phone numbers. That's because the first contact records added for these three had the phone data in them. Even though I flipped the sets in my intersection set, the result was the same, returning Robin, Mickey and Minnie. The ability to evaluate sets A intersect B and get the same result as B intersect A means that the intersect operation is a symmetric set operation. Union is also a symmetric operation. It doesn't matter if you do A union B or B union A, the final set of elements will both be the same set of names. Another useful evaluation might be to identify which elements are in one set but not the other. This is called a set difference. A difference subtracts elements in common from one set and another, leaving only the distinct elements from the first set as the result. This is an asymmetric operation because if we take set A and subtract set B from it, we'll end up with a different set of elements than if we take set B and subtract set A. The sets from these two operations won't result in the same elements. Let's see what this looks like in our code. I'm going to copy the intersect AB's three statements from lines 35 through 38 and paste a copy at the end of the main method. I'll change intersect AB to A-B on all three lines. On the second line, I'll change retain all to remove all. On the third line, I'll change the intersect character to a minus sign, and I'll just say this is emails, A minus phones, B. Running this code now, this shows us that Linus and Daffy are the only two records in the email list that aren't in the phones list. Now let me copy those last three statements and paste them right below. I want to change the set name A minus B in all three statements to B minus A. I'll also change the first statement and pass it phone contacts instead of email contacts to the constructor. The second statement, I want to pass email contacts there instead of phone contacts, so I'm reversing the direction, if you will. I'll change my header to say B minus A phones B minus emails A. Let's see what this gives us when I run it. As you can see, the set of contacts is a different set of characters altogether: Lucy Van Pelt, Charlie Brown, and Maid Marian. Let's look at what's called the set symmetric difference. This is really the union of the two asymmetric set differences. You can think of the set symmetric difference as the elements from all sets that don't intersect. On this slide, these are the elements that are represented in the paler yellow areas. This data can be retrieved in one of two ways. The first would be to do a union of our two different sets, A minus B and B minus A, so I'll do that next. I will set up a new set and call it symmetric diff, assigning it a new hash set and passing A minus B to that constructor. I'll call add all on the symmetric diff set and pass it B minus A. I'll print this out. Running that. I get the 5 contacts that don't intersect the union of my two asymmetric differences set. The other way to get these same set of elements is to take the union set and subtract the intersected set. I'll first create a set called symmetric diff2, a hash set constructed by passing the union AB set to it. I'll execute remove all on that set, passing it the intersect AB set, and I'll print it out. And running that now, I get the same results this way. Okay, so that covers the most common set operations and the difference between symmetric and asymmetric operations. I hope you can start to imagine how you might use these combinations to drive processing based on the relationships of the data in multiple sets. In the next video, I'll give you a set operations challenge to test what you learned, so let's move on to that.